Okay, let's start. Uh, Today, can you all hear me?
Yes.
Is it okay?
Yes.
Anyone respond?
Yes, teacher.
Okay, good. Yeah. I think today, okay, the Wi-Fi should be good enough. Okay. Yeah. So um, today I'm going to talk about how to solve Laplace equation with multiple GPUs, with multi GPUs. Okay. Yeah. Last time I talked about the vector addition with multi GPU. Okay. Um, in that case, okay, there are no communication between the GPUs. Okay. But for solving the Laplace equation, communication is necessary when we update the site, the field, okay, with the labels, okay, which are in the another GPU, okay. So in that case, any one of the GPU, when it goes to the boundary of the sublattice, okay, assigned to this GPU, then it need to access the field, okay, some field variables, okay, from the device memory, another GPU, okay. So in this case, okay, the peer-to-peer, okay, is very essential, crucial, okay, to get the good performance, good efficiency, okay, good speed up, okay. But last time when I talked about the vector addition, okay, there was some error in the CMD, okay, in this job description file. And I had used the one CPU, that means one CPU thread, okay, to do if I do the put two input files together in one CMD file, okay, one input file is for one GPU, the other is for two GPU. In that case, okay, the timing for the input and output for the two GPU would be wrong, because in that case, only one CPU has been used. Okay, only one OpenMP thread actually was used. So now the input, the CMD file and the output, okay, all this has been fixed in the directory vector and GPU. Okay, yeah, I will go to that later. Okay, let me first talk about the solve the Laplace equation with multi GPUs. Okay. Any questions so far? Oh, by the way, one of you uh, had has submitted a job, okay, which has some error, okay, and he produced a very large file, okay, and the job ran for about 15 hours or so, and so this, of course, is due to the code, okay, it's wrong, okay, something is wrong, okay, anyway, yeah. So I terminate your job and also remove your output file. Actually, the output file occupies 2 terabyte space. Okay, the entire directory has been full. Okay, so I have to remove that oversized file. Okay, so that is a erroneous. Okay, error. Okay. Um, from now on, I will impose the quota. Okay. So each one of you can only have 20 gigabyte disk space, okay? So I think for all your code, okay, and output, okay, it would occupy less than 20 gigabytes, okay? So in case you think 20 gigabyte is not sufficient, okay, let me know, okay? Yeah. Maybe I can increase your quota, say, from 20 to 40 gigabyte or so, okay? Yeah. But certainly, okay, your working space should be less than 100 gigabyte. Okay, yeah. No matter uh, how large is data set. Okay, for all the problem sets, okay, it won't require total together won't require more than 100 gigabyte. Okay, yeah. Also, I also limit your job time. Okay, start. Okay, will only be can upper limit is 1 hour. Okay, I think this is more than sufficient. Okay, for all the problems in the example code as well as the problem set. Okay, yeah. Then with this quota, okay, then you will not produce a file, okay, larger than say the 20 gigabyte, okay, because in that case you will stop, okay, and you cannot output a file, okay, too large. Also, if you have your CMD file or input file has some error, okay, then the job will terminate after 1 hour, okay. It will not stay in the queue forever, okay. Yeah. Okay. Yeah. So this has been discussed last time. So we have open MP threads, okay, to control M GPUs. Each thread control one GPU. Okay. Yeah. And now I want to solve the Laplace equation with multi GPUs. Okay. So for example, okay, this simple lattice, 10 by 10 lattice. And if I say use one GPU to take care of four sites, then I have I can, if I have a 25 GPUs, okay, then this is a 5 by 5, so 25 GPUs, okay. Then each GPU, okay, can handle the updating of only four sites, okay. Yeah. So this is example, okay. Yeah. So for 2D lattice, but of course in the GPU system, okay, we have, okay, for this course, okay, there are only two GPUs on the motherboard. So at most you can have two GPU. So in that case, you can either cut it this way or this way, okay? Cut it in the X direction or Y direction to have, okay? And that's it, okay? Yeah. But the sample code can be generalized to the general case. So any number of GPUs in X direction and any number of GPUs in the Y direction. Okay. Yeah. So let's talk about this in general. So this is the two-dimensional lattice, and then with the two-dimensional uh, uh, grid. Okay. Yeah. Of this GPU grid. Okay. Yeah. Yeah. So this is the first since this computation requires the communication between different GPUs, okay, and the GPU 0 has to access the device memory of GPU 1. So in the beginning, okay, I need to enable such that the peer-to-peer uh, can conduct, okay, can go on, okay, yeah. So this is a template to enable the peer-to-peer between neighboring GPUs, okay. So CPU IDX and CPU IDY. Okay, so actually this is the same as the Open MB Fed X and Open FMP Fed Y. Okay, and this is the yeah uh, position for the coordinate. Okay, for the GPU ID. Okay, CPU ID is the same as the GPU ID in this case. Okay, yeah. So first set up the number of threads. Okay, yeah, set the number of threads equal to the number of GPUs. Okay, and then for each OpenMP thread, it has this own CPU thread ID. Okay, so then this CPU thread ID, okay, can be decomposed into coordinate CPU ID X and CPU ID Y. Okay, yeah. So the decomposition is easy. Okay, depends on how many GPUs. Okay, in X direction. Okay, and then the numbering. Okay, is the counting the X first and then go to increase Y. Okay, so there's reason. Okay, so if I move the number of GPUs in X direction, then I get the is in the X direction. Okay, then you will get the position X. Okay, so if I divide by the number of GPUs, NGX. Okay, then I get the Y position. Okay, of the GPU. Okay, so so the position. Okay, or the coordinate of the GPU. Okay, can be fixed. Okay, or computed in this way. Okay. Then set the device, okay, to the set device. And then with the CPU thread ID, okay. So this is the array contains the GPU, the device number corresponding to the CPU thread ID, okay. Yeah, it could be just the same, okay. Device number is same as the CPU thread ID, okay. Yeah. Or could be different, okay. Up to your choice, okay. Up to your arrangement, okay. Yeah, I think in the most case, okay, the easiest way to just set the device number, okay, is equal to the CPU fed ID number. Okay, that's it. Yeah. Then uh, the right, okay, CPU R, okay, the right position, okay, the CPU ID of its right hand side of its right hand side, okay. So on the right hand side means the X position is increased by 1. Okay. Yeah, but since this is in the X direction, okay, the number of GPU cannot be bigger than the NGX. Okay, so I have to mode this. Okay, yeah. So the number CPU IDX, okay, is from 0 to NGX -1. Okay, so moving to the east right. Okay, the right is the CPU X. Okay, is increased by 1. Okay, and then move it with it. Okay, so if it's less than NGX, okay, then +1 will be fine. Okay, okay, yeah, yeah. If it's beyond the boundary, okay, then yeah, it would just uh, back to the yeah. So this is the more or less the imposed. This is the periodic. Okay, the right and left. Okay, yeah. And then plus this y position is the same. Okay, so just multiply this times the ngx. Okay, times this y position. Okay, so this gives the CPU ID of its right. Okay, the, that means the GPU. Okay, on this right, the ID. Okay, and then the CPU ID left. Okay, is the x position -1. Okay, and so on. Okay, then then the then I can enable, okay, here the CUDA device enable peer access, okay, of this device, okay. Yeah. So this is the device number, okay. Yeah. So in this case, this CPU ID, okay. Yeah, this the one with the CPU ID, okay. Yeah, yeah, this CPU thread ID, okay. Yeah, yeah. Can access the GPU on its right by after enable and enable the yeah. Let this left okay. Yeah. Here access okay. Let this right hand side GPU can access its device memory. Okay. And similarly for this command okay would enable this left hand side GPU to access its device memory. Okay. So now I have to let the top okay top GPU, okay, on its top, okay. So it's y position, okay, plus one, y coordinate plus one, okay. Yeah, and bottom is the y coordinate minus one, okay. So this is the CPU ID or GPU ID, okay, at its bottom, okay. And also turn on the enable the peer-to-peer access, okay, yeah, for this device, okay. Yeah. So now after this enable, okay, then each GPU, okay, can allow its neighbors, okay, neighboring GPUs, okay, to access its device memory, okay. So since this is for every CPU thread, okay, that means for every GPU, okay, such a enable is a set, okay, then that means every GPU can access the device memory of its neighboring GPUs, okay? Yeah. So this is the template to enable peer-to-peer between neighboring GPUs, okay? And this is the general way, okay, to enable the for the 2D, okay, for the number of GPUs in 2D on a 2D plane, okay, on a 2D grid, okay, yeah, and you can easily generalize this to three-dimensional or any dimensional you like, okay, but for the system you have, okay, yeah, say for example, in the DGX one, okay, you only have 8 GPUs on one motherboard, okay. So in that case, okay, then you can at most, okay, a three-dimensional, okay, 2 to the power 3, okay, is 8, okay, yeah, the grid, okay, yeah, yeah, okay, yeah. If you want to, yeah, if you have more GPUs, okay, say on different nodes, okay, you all take into account of this, and then if you have this uh and we link or and also this is a other communication device between different nodes, okay, yeah, then you may consider even have a high dimensional GPU grid, okay, yeah, but in most applications, I think 2D will be sufficient, okay, for almost all the purpose, okay, yeah, okay, yeah. Actually, in all my lattice QCD calculation, my GPUs, okay, 8 GPUs, and they always are arranged in one circle, okay, in a circle, okay. So that means this is a one-dimensional decomposition, right? Rather than two-dimensional or high-dimensional decomposition. Okay. So yeah, but I'm handling the four-dimensional lattice at five-dimensional lattice. Okay, so that means the this is unnecessary to decompose the entire lattice. Okay, uh, say suppose you have a five-dimensional lattice, then it is not necessary to decompose your lattice into say five-dimensional. Okay, each dimension you have to partition it. Okay, yeah, you may just partition one dimension, one of the dimensions, say pick one of the dimension, and then do the partition. Then the remaining lattice, okay, you have to handle that by one GPU is say four-dimensional. Okay, okay. So rather than the one-dimensional lattice. Okay, yeah. Um, okay. So this is the template, yeah, to enable the peer-to-peer access, okay, between neighboring GPUs. Okay. Yeah. Any questions? Hmm? Any questions? Okay. Uh, So let me recap how we solve the Laplace equation on a 2D lattice. Okay. So with any initial configuration satisfied boundary condition, we perform the iteration according to this uh, algorithm. Okay. So this is called the Jacobi algorithm. Okay, Jacobi iteration. Okay. So at each site, okay, I will update this site, this value, okay, this file, okay, by averaging over each label, okay. So each label, okay, x plus x plus one, x minus one, y plus one, and y minus one, okay. So that means the right, left, top, and bottom, okay. Add together and then divide by 4. So that's the average of its labels, okay. So I is the iteration number. Okay. So I plus one iteration is the replaced by the so I go through each lattice side and then replace it by the average of its labels. Okay. So say starting from this side, okay, and then move on and then move on and then update the file. Okay. And after this, okay, there is the one iteration. After going through each site, there's one iteration, and then the second iteration is again go from this side again. Okay, here the boundaries is fixed, so there's no need to update the boundary. Okay, yeah. So this iteration will continue until the difference, okay, of the new and the uh, successive iteration, the difference, okay, of the phi absolute value square, okay, and then sum over all the large size and then the square root of it, okay, is less than the stopping criteria, okay. So that is the knot of the error vector, okay. So there's the knot of the residue vector, and that's called the residue, okay. Yeah. So if the residue, okay, is less than the epsilon stopping criteria, okay, and this is usually we can say to 10 to minus 10, 10 to minus 11, or 10 to minus 12. Okay. Yeah, if this satisfies the stopping criteria, and then the iteration will stop. Okay. So the higher precision you impose, the more iteration it requires. Okay, and you take more times to obtain to attain the accuracy. Okay, yeah. Uh, Sometimes, okay, the convergence may be quite slow. Okay, and the speed of convergence depends on the algorithm. Okay, so the Jacobi iteration algorithm uh, is a rather uh, general, okay, yeah, and general purpose algorithm, okay, and we can design more efficient algorithms, okay, by changing our algorithm, okay, yeah, but at this moment, okay, let's just fix this to the Jacobi algorithm, okay. So in order to implement the iteration, okay, I need two arrays, okay. So this is the phi new and phi old, okay, and then switch the rows, okay, between these two array, okay. When I have the flat is true or flat is false, then I switch the phi, yeah, phi new and phi old, okay. So when true, then the iteration, and then phi old will, yeah, is phi zero, okay. Phi new is phi one, but then after it's updated, then I flip the logical flat to false, okay. Then I update uh, the phi one, okay, will be the phi new, and then I update the phi o from the phi new, okay. So it becomes the phi two, okay. So yeah, and each flag can handle the updating at each site, okay. Yeah, and that is the most essential part of doing the parallel computation and in the CUDA, okay. So uh, and each fed, okay, obtains the uh, difference, okay. yeah, of the of the successive iterations, okay, at each site, okay, and then the summation of each block, okay, yeah, is obtained by the parallel reduction, okay, and then this sum of the partial of the residue, okay, of from each block, okay, is passed uh, to the CPU, okay, to do the final summation, okay, so over all the blocks, okay, yeah. So the implementation, okay, yeah, for this two using the multiple GPU, okay, yeah, yeah. So first I have to declare the H new and H old, okay, there's a pointer to the working space, yeah, and then the H1, H2, okay. So this is the H1, H2 is the host field vector, okay, okay, and then HC is some of the uh, of the different square of this block, okay, yeah, after the parallel reduction. And GNU is the GPU solution, okay, and after they converge, okay, and then GPU solution is back to the sent back to the host, okay. And D1, D2, and DC is the device field vector, okay, yeah, 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 it is the store in the device, okay, and this is the pointer to a pointer because, yeah, I need to pass the address, okay, of this is the start of D1, okay, of this array, address of this array, okay, to, but I mean, I can be accessed by another GPU, okay, so this D1, D2 in the device, okay, is to declare as the pointer to a pointer. That means that this is, yeah, I need to know the, just pass the address of the device vector, okay, in another device, okay, yeah, such that another device can get this, okay, address, okay, from the correct position, correct address of the of any GPU, okay, neighboring GPUs, okay. Okay, similarly for this, okay, so this is the sum of the different square of each block, okay. Okay. So here I just point out the salient features, okay, of the implementation. And later I will show you the code explicitly, okay? Yeah, go through the code explicitly. So the number size, okay, is the index times ny, okay, and the size, okay, the of this lattice, okay, since each byte, okay, is a floating point number, so just the size is the how many bytes, okay, so times the size of float, okay, and the SB, okay, is the size of the shared memory, okay, so this is the block size, okay, bx times by, okay, so this is the yeah total number of threads in one block, okay, times the since this yeah uh, yeah this size of the flow, okay, yeah, because it's floating point number, okay, yeah, h1, yeah, h2 and hc, okay, in the host, okay, yeah, so this is the because this is the for the field, okay, so storing the data of the field, okay, so h1, h2, okay, yeah, so allocate this vector, okay, and hc, okay, is the contains the sum of the different square of each block, okay, so yeah, and GNU, okay, yeah, again, this is this is the uh, for the converged solution okay, 5, okay, after convergence, okay, and this is the will be uh, transferred from the CPU to the GPU, okay. So initially, okay, have you initialize the few vectors with the boundary conditions, okay, yeah. So first, when set this two arrays to 0, okay, and then set the boundary, okay, the one at the with this boundary condition, okay, yeah, at here, here. So initially set this to 0, okay, and then only set this boundary, okay, upper boundary, okay, to 1. Okay, so yeah, so here, so set to 1, okay, and then locate the working space for the GPUs, okay, yeah, and this is the size, okay, yeah, yeah. So this is the how many blocks, okay, bx and by. So this is the total number of blocks, okay. And tx is the tx in ty is the number of threads, okay, in each block, okay, in x and y direction, okay. So there's the size of the shared memory, okay, Sm, okay. And then the D1, D2, and the DC, okay, is in the device, the vector, okay, in the device memory, okay, yeah. So so D1, D1, D2, and DC, okay, yeah. Actually, this is the yeah, okay, yeah, allocate. This is the pointer of the pointer, okay. So since if I have n GPUs, then I should have n pointers, okay. Yeah, yeah. So and each pointer, okay, is a pointer or yeah, pointer of the array, okay. Yeah, pointer of the array, okay. So and since each GPU has one of this space, okay. So I need the allocated. This is the D1, D2, and DC. Okay, yeah. Of course, the size of the D1, D2, and DC. Okay, yeah, is uh, not the full size vector. Okay, yeah, as you will see. Okay, so this is memory allocation, cooldown memory allocation of this D1, D2, and DC. Okay, yeah, it's only the size divided by n GPU. Okay, see. So I have a yeah n GPU. Okay, yeah, and the entire vector. Okay, entire the vector of the entire lattice. Okay, yeah, is distributed to these n GPUs. So each GPU only has to get the 1 over n GPU of the size. Okay, this size is the how many bytes for the field 5 of the entire lattice. Okay, but the one of the GPU only take care of the 1 over n. Okay, of the updating of the field. Okay, so it only requires the this size. Okay, and each CPU thread ID. Okay, that means that each GPU. Okay, would have this D1, D2, and DC, okay, of the size, okay, this divided by the n GPU, okay. So this is the memory allocated to such a pointer, okay, or this of this space, okay, yeah. And then I have to copy the vectors from host memory to the device memory, okay, yeah. So H, Okay. So the copying mechanism looks like this. Okay. So it looks like okay. So I copy, for example, for this GPU. Okay, and this is same for each GPU. Okay, here I only just say take this GPU, for example. Okay, so for this GPU, it handles the lattice, this sublattice. Okay, so first I copy the this row by row. Okay, yeah, uh, uh, from a host. Okay, to the device. Okay, and the copy action, okay, is simultaneously for these NGPUs, okay, because each OpenMP thread is doing the copying, okay. So yeah, let me go back to code, okay, here, okay. So yeah, so this is LX and LY, okay, is the largest size in each GPU, okay. So each GPU, okay, so this is the copy, okay, a portion of the H1 H vector, okay, H, okay, this H1 has the CPU. H1 is the, you see, this is in the host, okay, yeah, H1, H2, and HC, okay. So H1 is the address of this vector, okay. So the address, okay, of H, okay, depends on which GPU it goes to, okay. So I have to add the offset, okay, for the GPU position. Okay, so this is the GPU position X times LX plus the GPU position Y times LY plus J. Okay, and this is J. Okay, yeah, is the J from 0 to J. Go through all these different uh, Y position. Okay, okay. So this is the exactly the say that this is copying the each row, okay, yeah, of the content, okay, from host to device, okay. Yeah. So this is the H, and the D, okay, is the device, okay. Again, for the device, okay, is the CPU thread ID plus the J times the LX, okay. And now when I do the copy, okay, I do the copy over this size LX times the size of float, okay, and this copy from the host to device, okay. So this is exactly the action as I will show you here. So I copy this and copy this, okay, yeah, from the host to the device for this device, okay, and different CPU thread, okay, doing the copy to different GPUs, okay, yeah, and then the so you copy the of the host vector at different location of the memory, okay, to the corresponding device, okay, which is assigned to this of this lattice data to this GPU, to the device memory of this GPU. Okay, so this is the how this code doing. Okay, and this for H1 and to the D1. Okay, to the D, okay, H to the D. Okay, yeah, and then this is H2. Okay, again to the of the D2. Okay, yeah. Okay. Any questions about it? Yeah. So before, for the vector addition, okay, we only have the one dimension, okay, and the number of GPUs is this is the in a one-dimensional array, okay, and now I have this two-dimensional array of GPUs, okay, and then so I have to this is the CPU fed. This is the GPU ID X and GPU ID Y, okay. So and the copy, okay, of data, okay, is instead of just a one-dimensional array, okay, I have to do it some of the all this row, okay. So this is the two-dimensional, okay. Yeah, array, okay, but it is not a continuous array, okay, in 2 dimensions, okay. So that's the reason why I have to do it each row horizontally, okay. Yeah, for different y, okay, for different j, okay, yeah, okay. Yeah, for the if it's only a one-dimensional array of the GPUs, and then it's easy, okay, just copy it. Yeah, as what we have done in the case of the of the um, of the of the vector addition. Okay, in that case, then I just copy just once. Okay, one-dimensional array. Okay, but since it's a two-dimensional data, okay, and they are not contiguous. Okay, not so we have to do it separately. Okay, yeah, using this two rule. Okay. So after the post data, okay, initial file uh, of the entire lattice has copied to each GPU, corresponding GPU corresponding to this uh, uh, decomposition. Okay, yeah, to its partition. Okay, then we can do the iteration. Okay, perform the iteration. Okay, so this is the loop. Okay, so if the error, okay, bigger than the stopping criteria, the epsilon, okay, and also the iteration less than the maximum, okay, then each thread, okay, CPU thread, okay, each GPU, okay, yeah, okay, will do the following, okay, according to this its own GPU ID, okay, CPU thread ID, yeah. So so the CPU thread ID, okay, is obtained from the OpenMP, okay, get thread number, okay, yeah, and then the CPU IDX, okay, yeah, as I said before, okay, yeah, because it's a two-dimensional grid of the GPU, so just the X position, okay, can just be molded by the number of GPUs in X direction, okay, yeah, and then the Y position of this GPU is just divided by the N number of X number of GPUs in the X direction, okay, so. And then after that, I can set the device, okay, to this device number, okay, so of this device number, okay, or in the simplest case, okay, the device number is the same as the CPU fed ID, and that's the set the CPU ID fed, okay, the device with the CPU fed ID, okay, yeah, and okay, there's a DO and D new, okay, yeah, yeah, and then also the DO, okay, uh, uh, left, okay, right, D device vector, left, right, top, and bottom, and O, okay. And this the D0 O and the D0 new, okay. Yeah. So the DO and D new, okay, choosing, okay, from the D1 and D2 according to the thread, okay. If the thread is true, okay, then the DO is the same as the D1, okay. Yeah. Otherwise, if thread is false, okay, then it's D2, okay. Yeah, for the D new, okay, it's just opposite of it. Okay, so if that is true, then d nu is equal to d2. Okay, so that means that O and nu, okay, yeah, always different. Okay, either choose D1 or D2. Okay, but yeah, they always depends on the fact is true or false. Okay, is flipped. Okay, so so the D0O. Okay, so this is the DO. Okay, yeah, with the CPU flat ID. Okay, yeah, and the D0 new. Okay, is the D new of the CPU flat ID. Okay. Okay. Um, Now, yeah, this D1 and D2, okay, is required, okay, since I need to get the device, the memory, okay, from this label, okay, so from this label, when it goes, when it comes to the boundary, okay, yeah. So I need to know the DLO, okay, the left, okay, left, right, bottom, and top, okay. So, but for each CPU, okay, uh, is yeah, left, okay, or right, okay, yeah, some of the GPU, okay, may be at the boundary, okay, yeah. In that case, okay, uh, then it does not have uh, the right, the left, uh, the left, okay, GPU, okay, you see, yeah, for example, okay, here. Now, if this, it has a GPU X, okay, CPU ID X, okay, 0, okay. So it does not have this, it does not have the left GPU, okay. So yeah, so, and similarly for this one, it does not have the GPU on this right, okay. And for this one, it does not have GPU on this top, okay. And for this GPU, it does not have the GPU on the bottom, okay. But for this GPU, it has both left, right, top, and bottom, okay. So, um, so, so for the CPU flat ID X position is equal to 0. That means it does not have left, okay. It already the left, the most left, okay, position, okay. So if this is 0, okay, then aside the new, okay, that means yeah, it does not have the left, okay, yeah. Otherwise, the D left, okay, O, okay, is equal to DO of this CPU ID minus 1, okay. And then the Y position, okay, just use the Y position, the same, okay, because in the X left, okay, left is the shift X by 1, okay, position by 1. So the Y position, okay, is the same, and then times the N GPU X, okay. Since I use this one-dimensional number, okay, so to using this, so decomposed to the X and Y position, okay, so the numbering, okay, the numbering, okay, from 0, 1, 2, 3, 4, and so on to 24, okay. And these numbers, okay, any of this GPU number, okay, has its position, X and Y position, okay. So yeah, for this one is X is position 0, okay, and then the Y position is also 0, okay. So for this one is X is 1, Y is 0, okay. For this one is yeah, X equal to 4 and Y is equal to 4, okay, yeah, okay. So I just use this uh, 24, okay, to compose it, okay, in the when I divide by the 24 divide by 5, okay, then more it, then I get 4, okay, that's solution 4, okay. So 24 divided by 5, okay, then I got 4. Okay, again, okay, because the integer. Okay, so 4. Okay, so I get the position y. Okay, it's 4. Okay, yeah. So this is how the yeah. So this is the x and y. Okay, yeah. Get the GPU ID. Okay, yeah, from this x and y position. Okay, okay. The right, okay, is the x position plus 1. Okay, and then the bottom is the y position minus 1. Okay, and then the top is the y position plus 1. Okay, now, yeah, and yeah, the when the GPU in the at the boundary, okay, and then it does not have the left or does not have the right, does not have left, then it will give me the new vector. Okay, so you will not give me some address, okay, which is not does not existing. Okay. After that, then I can call the kernel. Okay, yeah, Laplacian, and then give the block size, the number of blocks, okay, in the grid, and then the how many threads in the block, okay, and the size of the shared memory, okay, okay, and after this, then I have the O, D left O, okay, D right O, DBO, DTO, and then the DCO new, okay, and then and then the CPU. This is a DC, okay, yeah, for the sum of the different square, okay, yeah, yeah. Yeah, of each block, okay, and yeah, okay. After this, okay, then I have to uh, synchronize all the GPU first, okay, screw the device, synchronize, yeah, okay, yeah, yeah. So you see, this is the kernel, okay, executed by each GPU and by each block, okay, yeah. So yeah, in this case, I have to synchronize the device, yeah, all the GPU synchronize it, okay, yeah. And then I copy the memory, okay, from the all this data, okay, from device to host, okay. So in coupling this, okay, I'm aware, okay, different GPU, okay, copy to the different position, different address in the host. So I have to give it this array or is the offset, okay. So this is the XC plus the BX times BY divided by N GPU, okay, this divided by N. And then this number times the CPU for ID, okay, yeah. So this is the position, okay, of this DC, okay, goes to the host, okay, HC, okay. So this is the DC with the CPU flat ID, okay, and then the size is the SB, okay. SB is the total of this share memory, okay, yeah, yeah, and then divided by the n GPUs, okay, yeah. So each GPU give some of the um, uh, a puzzle, okay, of some of the different square, okay, yeah. So, this is the yeah end of the OpenMP, okay. So this is the computation involves the using OpenMP, okay, to control these NGPUs to perform the computation, yeah, together in parallel, okay, yeah, and then yeah, in this kernel, okay, yeah, it requires the communication or compared, it requires the peer-to-peer access the communication between the different GPUs. Okay, when the updating, okay, yeah, at the boundary of the lattice sublattice of each GPU. Okay, and then this part is the computed by the CPU. Okay, some of the all the HC. Okay, yeah, this is the some of the um, each block. Okay, all the blocks. Okay, yeah, yeah, errors. Okay, all blocks. Yeah. Okay. So this is the how many number of blocks? Okay. Yeah. Bx times by is the total number of blocks of this in this grid. Okay. So so this gives me the sum of the phi I minus phi I plus one absolute value square and sum over all the lattice size. Okay. And then the taking square root is the residue. And then this is the and then it will check, okay, whether error is bigger than the stopping criteria. If yes, then and also iteration is less than the maximum number, then you would do this loop again. Okay, that means you will increase the iteration by one, and then the flag, okay, is changed from the opposite of the flag before. Okay, that means from true to false or from false to true. Okay? Yeah. So this is the execute in the host. Okay, yeah, and then by each OpenMP thread. Okay, yeah, and now we go to this kernel. Okay, the kernel. Yeah, the kernel is okay. Okay, so this is still the in the host code. Okay. So this is the copy results from the device memory to the host memory. Okay, yeah. So after the iteration is converged, okay, exit this after this loop is exited, okay, yeah. Then we have copied the results, okay, from the device memory to the host memory, okay, yeah. So again, okay, we have to use the OpenMP, okay, using MFES, okay, to do the copy simultaneously, in parallel, okay, yeah. So this is the GPU ID X X position, X coordinate, and the GPU Y coordinate, okay. And then the CPU fat ID, okay, and then we can obtain the X position and Y position, okay, by this, okay, once from the CPU fat ID, okay, and then set the device, okay, yeah, according to this CPU fat ID, okay, and it can be represented in the array, okay, yeah, and that is the mapping, okay, which may be different from the device number, may be different from the CPU fat ID, okay, but yeah, yeah, it's easier to say the device number just equal to the CPU fat ID. Yeah. So the DNU, okay, yeah, will we will assign the DNU, okay, we assign the DNU, okay, to the D1 or D2, okay, yeah, yeah, depends on the flat, okay. I will flip it between the, I flip it to the D2 as a, yeah, if flat is true, then the D2 is the D new, okay, and then okay, if flat is false, okay, then the D new is D1, okay, yeah. So So this is the according to the here. Okay. Yeah. The same. Okay. This is D new DO. Okay. DO is the true. Okay. Is the D1. D new. Okay. Is true. Okay. Is the D2. Okay. So here. Okay. Yeah. D new. Okay. If that is true. Okay. That's the D2. Okay. Otherwise, that is a D1. Okay. Yeah. So you see, okay, this is the DO, D new, okay, here is a D2, okay, yeah. D new is a D2, okay, so it's the, yeah, same as the in here, okay, in here, okay, yeah. So the G is G new, okay, and plus this, okay, plus this is the depends on the GPU position X and Y, okay, yeah. And then the D new, okay, is this. This is the host, okay. So this is the in the device, okay. So in the device, I have to copy it to the in the host, okay, copy it to the different portion of the G, okay. Depends on the GPU, which GPU, okay. So yeah. So this is the copy, okay, from the device to the host, okay, from D to G, okay. So it copies to the different location in the array G, okay, yeah. Depends on the CPU CPU ID X and CPU ID Y, okay. And after that, then I can feed the device memory D1, D2, and DC. Yeah. Okay. Uh, any questions about the host code? Okay. Now, let me turn to the kernel. Okay. So this is the kernel executed by the GPU and for each thread, okay, yeah, of a block, okay, or each block. Okay. So uh, here, okay, the cache, okay, is the share memory, okay, fixed by the kernel, okay, the kernel, the yeah, when I SM, okay, so this is the size, okay, yeah, here, okay. And the top left, center, right, and bottom, and the difference, okay, and the side, okay, uh, side, okay, is the uh, position, okay, in the sublattice in of each GPU, okay. And then there's a skip, okay, is when it's at the boundary, okay, then I don't have to update it because at boundary, okay, the value 5 is fixed, okay. The field variable, okay, at the boundary is fixed, okay. So in that case, I don't have to update its value at all, okay. So for each GPU, the sublattice size is the LX and LY, okay. So each, yeah, so this is the dimensions, the block X block times the width, okay. So yeah, so this is the size, okay, yeah, of the each sublattice, okay, yeah. In each GPU, okay, there would be many blocks, okay, yeah, in the grid. Okay, so each block has each dimension. Okay, so in X direction, okay, you have the Lx. In the Y direction, the size of the sublattice is L1. Okay, okay. So this is the total number of threads. Okay, in X direction, Y direction of this grid. Okay, or the lattice sublattice handled by this grid. Okay, and the position in this sublattice. Okay, uh, uh, each thread. Okay, thread ID. Okay, has thread ID X and Y. Okay, so you would handling the file update with the X position and Y position in this sublattice. Okay, so for the cache lattice, so for cache index, okay, uh, just this thread ID. Okay, yeah. So this in this the block. Okay, for each block. Okay, so is the thread ID X plus the thread ID Y times the block dimension X. Okay. So the position, linear position, okay, site, okay, of in this sublattice, okay, is the X plus Y times Lx. Okay. Initially, I set the skip equal to 0. Okay. Yeah. And then the difference is equal to 0. And then all the bottom, left, right, and top field, okay, initially to be 0. Okay. Yeah. And the C, okay, is center. Okay, the phi IO at the site. Yeah. So if X equal to 0, okay, so that means the left boundary of the sublattice. Okay, but this left boundary of sublattice may be at for the GPU. Okay, at the left boundary of the entire lattice. Then I don't have to update this site at all. Okay. Yeah. So if X equals 0, okay, so there's the left boundary of the sublattice. And then I have to make sure that I have to see whether it is at the left boundary of the entire lattice. Okay, yeah. If this is yes, okay, because the phi I L O, okay, this will be equal to new, okay, when is at the boundary. Okay, so there's no left at all. Okay, yeah. So I know, yeah, if this is equal to new, okay, then it must be at the left boundary of the entire lattice. Okay, if not, then it's not at the this GPU. Okay, it's not at the, yeah. So the yeah, it's not at the left boundary. Okay, at the left boundary of the entire lattice. Okay, yeah. So yeah, X equal 0 is the left boundary of the sublattice. Okay. Yeah, and X equal 0 would exist in every GPU, okay? But only for the GPU at the left boundary of the entire lattice, okay, is left phi left O, okay, is equal to new, okay? You see? Yeah, this is the in the here, okay? I said here, okay, uh, okay, okay, yeah, here, okay. DLO, okay, you see. So when the CPU thread ID equals 0, okay, then that means this GPU, okay, X position is already at the X equals 0, okay. So that means there's no another GPU and on this left hand side. So set to the new, okay. So it won't go. It does not have any address at all, okay. Yeah. Similarly for the right bottom top, okay. Yeah. So so this is the something we have to handle when we have a multiple GPUs, okay? Because which GPU does this GPU, yeah, whether it's in the left boundary of the entire lattice, okay? Yeah. So then in this case, it's skip, okay, skip, okay. Yeah, so set this skip equal to 1, okay? So if it is in the left boundary of the entire lattice, then I don't have to update this site, okay? Yeah. So similarly, okay, yeah, the other, okay, if not, okay, that means the it has a GPU on the left, okay, and is EX equal to 0. So in that case, okay, yeah, then this left, okay, is in another GPU, okay, so it's yeah, yeah, not and so if yeah X equals 0, okay, then left is a phi LO, okay, so you see you have to assess, okay, assess this, okay, value, okay, from this from the phi LO, okay, is in another GPU, okay, the left GPU, okay, phi phi L, okay, L is that's the on the left hand side, okay, of left GPU, okay, yeah, and the phi 0, okay, is in this GPU, okay, yeah, and this side plus 1, okay, so that means when this GPU, okay, yeah, the left boundary of the sublattice, okay, then its left, okay, has to obtain phi value has to obtain it from another GPU. Phi LO is from the its left GPU, okay, yeah. Phi 0 O is in this GPU itself, okay. So to access the data here, it would use the peer-to-peer access, okay, because this already turned on the peer-to-peer access in the beginning, so that each GPU can access its labels, okay. Yeah. Okay. So is this clear? Hmm? Yeah. So that the entire setup looks a little bit complicated than before, okay, but it's still quite transparent and manageable, right? Yeah, it's quite straightforward actually. Yeah. Yeah. So now it's in the left boundary, and then I have to see if this is in the right boundary. Okay, so this is the same consideration. Okay, if the phi R O, okay, is not equal to nil, that means it's not at the right boundary. Okay, yeah. If it's right boundary, then it's right. Okay, must be a phi right O must be a new vector. Okay, so in that case, okay, it skip. Okay, yeah. Otherwise, okay, it get this left hand side. Okay, is in this GPU itself, okay. But its right hand side, okay, is in the device memory, okay, of the another GPU, okay. So it's a phi IRO, okay. R here means the the this is the right hand side, okay. Yeah, but it's a GPU, okay. O, okay. Yeah, array, okay. Okay. So this data is obtained from the uh, right-hand side GPU, and this is data is obtained from itself. Okay, yeah. So 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 yeah, this is the X and Y position. X and Y. Okay, so I have to test whether it's the X position and Y position. Okay, is at the upper boundary or the lower boundary. Okay, yeah, and then similarly for the left hand side and the right hand side. Okay, so these are taking care of all these uh, GPU. Okay, no matter which GPU. Okay, on the boundary or inside, okay, then it is handled properly, okay. So now after all this, okay, then if skip equal 0, okay, that means it's not this side, okay, it's not at the boundary of the entire lattice, okay, not at the left boundary, not in the right boundary or top or bottom boundary of the entire lattice, okay. So in that case, okay, then this side, the phi of this side can be updated, okay, should be updated. Only at the boundary of the entire lattice, okay, is fixed, does not need to update, okay. So if skip equals 0, that means none of this side is not on the boundary of the entire lattice. And then I can do the updating, okay. But I do new equal to this, okay. Yeah. Yeah, if this GPU handling lattice, okay, which is at this not at the boundary at all, then yeah, it would go to in all cases, it would go to this and this, okay, yeah, yeah, and then it updates according to this. Okay. So yeah, so this is just the yeah. In that case, it's just a normal case, okay. Yeah, get everything from the yeah either from the file itself or from the its neighboring GPU. Okay. Yeah. Okay. Yeah. Okay. Yeah. Any question about this? Hmm? You see,
Professor,
yes.
Suppose the GPU is at the upper boundary. Why don't we add the other three value? Like, but we sum up.
No. Upper when if I have a no, if you are x and y, x, okay, for example, x, okay, yeah, then you are at the boundary of the left boundary of the sublattice, but not necessarily at the left boundary of the entire lattice. So I have to see, okay, whether it's in the left boundary of the entire lattice, okay? Yeah, if phi LO is equal to nu, then is then is in the left boundary of the entire lattice, okay? Okay, then I go to this, okay? Only when it is not equal to nu, then I know, okay, its left boundary, okay, is not the left boundary of this sublattice. Is not the left boundary of the entire lattice, okay? Yeah. So I have this left and the right, okay? In this case, okay, then the left, okay, is obtained from another GPU, okay? Yeah. So the bound, you see, yeah, when at the boundary of the entire lattice, okay, I don't have to update at all, so you have to skip it, okay?
Okay.
Yeah. So you see, when it's not the case, and also not this case, okay, then the left and the right, okay, yeah. So it's not at the at the boundary of this sublattice, then it can up its left and right is in this same device. This 50O and 50, yeah, is side -1 and side +1. Okay. Yeah. Okay. Now for the Y, okay, for the Y, okay, case, okay, if the Y is 0, okay, or Y equal to this, then I can see, okay, whether yeah is so if it's Y equals 0, okay, then the bottom, okay, yeah, if it's not at the boundary of the lattice, okay, then this bottom, okay, yeah, is obtained from another GPU, okay, and this top is getting from this GPU itself, okay, yeah, and similarly for the top, okay, yeah, for the top, okay, yeah, the bottom, okay, yeah, 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 is from itself, okay, yeah, and then if it's not at the boundary, is if y is equal to that means that at the top of this sublattice, okay, then this top must, yeah, the top of it, okay, must be in another GPU. So I have to get this data from the another GPU, 5T0, okay, yeah. You see, the 5.0 is from this GPU, okay, 5T0 or 5TL, 5TB or 5T, yeah, uh, uh, yeah, 5TR, right? Yeah, 5R, okay, 5R, okay, and 5R, 5T, 5B, okay, 5L, okay, yeah, from another GPU, okay, yeah, provided, okay, this position X and Y are not in the at the boundary, okay, of the lattice, entire lattice, okay, yeah, so, okay, so after that, after this assignment, then we can check whether the skip is 0, 0. Skip is equal to 0, okay. Then that means if does not is not the site of the boundary of the entire lattice. So I can do the updating. Okay. You see? Then I can add this together. Okay. Yeah. So if it's not at the boundary of the entire lattice, then this BLRT, okay, could be from the same GPU, or from some of data from this neighboring GPU. Okay, one of the data from one of the neighboring GPU. Okay, yeah, yeah. So these are the case. Okay, you see, let me go to here. Okay, so if I go to at this site here, okay, then is x equal 0, okay, and x equal 0, but then yeah, it's not the boundary. This is not the boundary of the entire lattice, okay? This is not this, okay? So I can get its neighboring the depth, okay, from this GPU, from another GPU here, okay? Yeah. And similarly, if I go to here, then I get the left bottom from another two GPU, okay? And from the top and the right, okay, from this GPU, okay? And then I update the file here, okay? You see? So for this GPU, okay, none of the site, okay, are on the boundary of the entire lattice, okay? So every site has to be updated, okay? Now, if I go to this GPU, for this GPU, okay, then when I come to this site, okay, because this 4 site, okay, handled by this GPU. But this site is at the boundary of the entire lattice. So you will just stop. Okay, skip it. You will just skip. When it comes to this site, okay, you will skip. Okay. When it comes to this site, you will skip it. Okay. Yeah, because this five top, okay, 5T, okay, O, okay, is a new vector, okay, without any address, okay. Similar for this, the 5R O does not have any address, okay. So it's skipped. Okay. So for this three site, okay, is left, right, or top. Okay. Uh, file address. That means this does not have a device. Does not have a device. Okay, on this top, on this left. Okay. So for this size will be skipped. Only this side. Okay, here. Only this side. Okay. Yeah. Uh, for these two value, okay, it can access from this GPU. Okay. For this bottom and the left, access from another GPU here, and also another GPU here. Okay. Okay. So this view value has to update it. Okay. So this is explicitly how this code, okay, would execute. Okay. Yeah. Okay. Uh, is this clear to you? Hmm? Yeah.
Okay,
No?
okay.
Huh?
I see, I see.
You see it?
Yeah, yeah, yeah.
Okay.
Thank
Yeah. I think it's not too difficult to understand every steps. Okay. Yeah. Yeah. But you may have to think it again. Okay. And yeah, it's not trivial, but it's not too non-trivial. Okay. As I said. Okay. Yeah. So it's reasonable. It can be understood. Okay. And the logic is quite obvious. Okay. Yeah. Because we have, I mean, the many GPUs. Okay. So, and we have to access the data. Okay, from this neighboring GPU. Okay, when we come to the lattice site on the boundary of this sublattice handled by each GPU. Okay, so for the and with the global with this global boundary condition of the entire lattice, okay, is fixed. Okay, then this is the way how I can use the multiple GPU on a two-dimensional lattice, and then with a two-dimensional decomposition. Okay, yeah, and this decomposition also works. Okay, if I only have two GPUs, I can decompose it in the x direction or in the y direction. Okay, partition it. Okay, either way. Okay, it will work. Okay. So that means the code works for the one-dimensional partition or two-dimensional partition. Okay, one-dimensional partition either in x direction or in y direction is okay. Okay, yeah. Okay, yeah. Okay. Now, so the rest should be uh, obvious because this pair reduction is the same as before. Okay, yeah, and that's what for is done for each block. Okay, and then partial sum of each block. Okay, to see. Okay, yeah, or everything depends on the GPU ID. Okay, has been outlined. Okay, yeah, copy the result from the device memory to host memory, and different GPU data. Okay, goes to the different position of the host vector. Okay, yeah, and uh, this is the GNU. Okay, in the host. Okay, and depends on which GPU ID. Okay, this GPU position. Okay, X and Y. Okay, in this two-dimensional GPU grid. Okay, so and for each device vector you need for each GPU, okay, you always this case, okay, yeah, and I copy this, okay, yeah, to the host vector. Okay, so copy the results. Okay, the converted field vector. Okay, to the host. Okay, so but yeah, and copy it to the different position. Okay, and the copying action is the same as the copy from the host to device. Okay, it's for 1 row, 2 row, 3 row. Okay, the same as here. Okay, just copy it. Okay, from yeah, for this GPU, you copy this row. Okay, to the host, and then copy this row to the host. Okay, that's it. Yeah, and similarly, yeah, for the for the initial data from the initial file, copy from the host to device. Okay, also the same. Okay, yeah, first this and then this. Okay, okay, yeah. So this is the way copying data from the copying the file. Okay, from the host to device and vice versa. Okay. Yeah. Yeah. Here you can see. Okay. Uh, for the updating here for the kernel for each kernel. Okay. Yeah. For each thread. Okay. For the kernel. I always use the file new update from the file O. Okay. Yeah. From new update from O. Okay. And I have switched the role. Okay. Of the new of the not I'm not doing it the flip flop. Okay. The selection. Okay. Actually, that is from the here from the D1 and D2. Okay. Here. Yeah. Yeah. And it is you see it was the in the chip in the host code here. Okay. Yeah. DLO. Yeah. This is the here. Okay. DO and D new. Okay. Yeah. I would already assign to the D1 and D2. Okay. So yeah. Actually, yeah. What is the changed? Okay. Is the O and new. I always update the new from O. Okay. But then the depends on the Fed. Okay. I would choose D1 or D2. Okay. So actually, what is changed is the D1 and D2. Okay. Here. Okay. Yeah. And so I can always update the D new from the DO since the Fed. Okay. Changes. Okay. So yeah, when it's the true, then yes, this is the D1 and D2. When it's false, okay, it's the D2 and D1. Okay. So yeah. And D1 and D2 is always yeah in the yeah in the device. Okay. Yeah. And so is the DO and DU. Okay. Yeah. But I don't have to change the code itself. Okay. Because yeah yeah and the kernel here I always have one loop. Okay. I don't have the yeah the thread. Okay. The thread is not entered in the code, the kernel code here. Okay. Yeah. Okay. Here, the updating also define new. Okay, 50 new. Okay, yeah, updated. Okay, by this. Okay, okay, yeah. Um, yeah, the complete code is here. Okay, you can look at it. Okay, yeah. Now I think I can go to the TLCP1. Okay, to go to the complete code. Okay. Let me switch the screen. Okay. Yeah. Let me see. Okay, it still works. Okay, so let me see. Let me stop this screen and then use the connect to the new screen here. Okay, now you see the TLCP1 terminal. Okay. Yeah. Before I talk about this lattice 2D and GPU, let me go back to the vector add. Okay, and GPU. Okay, yeah, and now I have a free CMD file. Okay, yeah, CMD G1 is only one GPU. Okay, so here I request the CPU equal to 1. Okay, in that case, okay, I only use the one open amplifier. Okay, to control one GPU. Okay, and then the argument here. Okay, is a vector add n GPU and then input G1 and output G1. Okay, yeah. And for the GPU 2 CMDG2, then I have to use the GPU CPU is 2. Okay, yeah. And then the so this is the execute this. Okay, I have to. Okay, and now if I can doing this two input file together in one CMD file. Okay. In that case, I must use the G2 using request CPU is 2. Okay. Here. And then here, I use, so this is the input file 1. Okay. And when this is completed, okay, then the output is to here. Okay. And then it will execute with, using the input G2, okay, and then again the output go to here, okay. So this is the how you can have many input files in one CMD file, okay. Yeah, but the number of CPU here must be the largest number required by the input file here, okay. You see, once you set the request, the two CPUs, then the condo will assign 2 GPUs to your job. Okay. Yeah. You use request 1, then you will only use assign 1 GPU and only using one open amplifier. Okay. Yeah. So uh, yeah. So in case when you have many input files, okay, with different number of GPUs, then you should always use it, request the number of GPUs to the largest number. Okay. Yeah. Okay. So let me remove the output file first. Okay. So that you can see the clearly. Okay. Okay. So condo submit. Okay. GMD G1. Okay. Okay, now, and then submit G2. Okay, now I can submit two jobs, okay, together, and they just queuing, okay. You see, this is the one job and two job, and then these two jobs actually with the two different input file, okay, CMD G1 and the CMD G2, and now this is the I think this is already done. Both of them are done now. Okay, now this is executing in the TFQCD 218. Okay, and then let me see again. Okay, okay. So this is done very fast. Okay, and this using one GPU, and now second job is using two GPU. Okay, so done. Okay, okay, done. Okay, now let me look at the output file. Okay, output G1. Okay, so this is the output G1. Okay, one GPU. Okay, it took you see the input time. Okay, 152 millisecond. Processing time 32 seconds, and the output time is okay. Now let's the G2. Okay. Now compare the input data input time for the one GPU is 152. Now the input time for the two 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 GPU or using O2 Open MP fab, okay, is only 76. Okay, this is only half of the time here. Okay, so this is how this Open MP works properly. Okay, yeah. Similar for the data output time, 140 millisecond. Okay, this only 81. Not half, okay, but almost reduced by a factor of 2. Okay, yeah. And the total time for the GPU is this is 173 millisecond, and this 324. So this is almost reduced by a factor of 2. Okay, so for in terms of speed up, okay, this 1.6 is the 3.0. Not perfect, okay, not a perfect 2 speed up, okay, but it's quite close, okay. Yeah, 3.2. So yeah, it's the 9, okay, yeah, okay, 1.9, okay, yeah. So 1.8, 1.9, okay, yeah. So now I can submit this two input to G1 and G2. Okay, input with the G1 and input with the G2. Okay, one GPU and two GPU together. On those submit. Submit. CMD. Okay, G1 and G2. Okay. Now, so you would first execute the one with the G1 input file, and then execute the input with the G2 file. Okay. Now the input G1 is this. Okay, here I use the GPU ID 1. Okay, yeah, you can use GPU ID or using GPU ID 1. Okay, it gives you just assign a GPU ID number by the control system. And the input G2, okay, here. Then I have the 0 and 1, okay. But I can also input here, G2 here, is this, using the GPU ID1 and the GPU ID2. And then you assign two GPU ID here, either 01 or 10, okay, up to the control system. Okay. Yeah. Anyway, if I look at the output here, output G1, G2. Okay. You see, yeah, this is exactly the same one I have submitted using the one GPU and the two GPU results. Okay. Yeah. And they are half of the input and output time, okay, of the one GPU, and also the speed up here, okay, is a is a factor 2. Okay. So let me remove this output T1 T2 and resubmit job again T1 T2 because I have changed the uh, the input file. Okay. T1 T2 still not done yet. Okay. Is it the most of okay now done? Most of the time is in the let's see how come it's not there. G1 G2. Let me see. Output G1 G2. Input G1 input G2. Input B2 G2. Yeah. CPU ID1 CPU ID2. Let me see. It says some here. It's done here. G1 and G2. Okay, here. You see, this is the 154. Seems to me this is not input time is data input time here looks strange, okay, because this you see this is 157 and this is the 161. And output time is reduced by a factor 2, but the input time is not reduced by a factor 2. It's something looks strange. And also the speed up for it. Yeah. So I don't know what happened in here. Presumably, you should give me the output. Something seems to be wrong here. I'm not sure. I will do it again. So in this case, for G2, I assign this G1 and G2. Okay. Now, see. Okay. Yeah. The reduction here is not reasonable. Okay. So I don't know why. Let me change it to G2 again. So for input GGID, so in this case, then if I switch it to the 0 and 1, then it would be different. That's what I saw last time. Input 2. Let me see. G1, G2. Yeah. Yeah, there's still something strange about this condo setting. Suppose you can see that you can GPU1, GPU2 should be okay. You assign the GPU number, but then for the OpenMP, okay, yeah. You see, for this now this time is correct, okay. This 78, okay. So seems to me the input for a 2 GPU, one has to be assigned the number explicitly 0 and 1, okay. I think there's something there's still a bug in the condo submitting system, okay. Yeah, maybe this can be fixed, okay, later. Then I can use the GPU ID1 and GPU ID2 to replace the 0 and 1, okay. But for the moment, okay, just for the 2 GPU case, just use the 0 and 1, okay. Yeah. I think I run out of the time for today's lecture, okay. So next time I will go to the Laplace 2D and GPU, and then I will go through the code and also the look at the input and output file. Okay, here. For here, I have the three input files. Okay, together at the same time. Okay, yeah. So first is the one GPU. Okay, and the lattice. Okay, is the here. Okay. Yeah. So this is for the two-dimensional decomposition. So that means the number of GPU X direction and Y direction is 1. And the GPU ID was selected by the condo is 0, okay? And the lattice size is 1024, 1012. And then the number of threads is 32, 32. So the grid size is 32, 32. Okay. Grid size, the dimension of grid, okay, is 32, 32. Okay. So 32 times 32 is 1024. Okay. And in this case, it's better not to compute the CPU vector solution because the CPU takes a long time. Okay. So the total iteration, and this is a processing time, and the gigaflop is 43 gigaflop. Okay. And now for total time for the GPU is this. Okay. Yeah. Now if I using 2 GPU, okay. Yeah. And then you see the data input time is only 7 millisecond. Okay. Compared to this one is 11. Okay, so it's reduced. Okay, and now look at the processing time. Okay, for Laplace equation. Okay, the most time consuming part is doing this iteration. Say how many iterations, and then the number of iterations. For this 1024 by 1024 lattice is about about 1,400 seconds. Okay, so iterations. Okay, the time is about 238 seconds. Okay, yeah. So about 4 minutes to 4 minutes or so. 40 more than 4 minutes. Okay, and now if I use 2 GPU, okay, the gigaflops is 75. Okay, about 1.8. Okay, and the total time, okay, is almost by a factor of one reduced by a factor of 1.8 or 1.9. Okay, so total time is this 135 second, and this is the 238 second. Okay, so you can see the two GPUs speed up. Okay, yeah, and the output output field configuration. Okay, yeah. Since I do not rename the field configurations, so the file output is this, okay, and it has been overridden by the one GPU and the two GPU, okay, solution, okay, so yeah, okay, I really run out of the time, okay, so so I'll go through the code again, and then you can go ahead to try this sample code, okay, but this sample code takes some time, okay, yeah, I'll remove this, and then I those submit GMD. G1. Okay. So you take about, yeah, some, yeah, 5 minutes, 6 minutes. Yeah, about that. Yeah. Because it takes about, yeah, 4, yeah. Yeah, about, yeah, 300, 400, yeah, maybe the total time, okay, for the one GPU about 300 something seconds, okay, and for the so about 5 minutes, and then another for two GPU about 2 something minutes, so about 7 or 8 minutes, okay, so yeah, take some time, okay, to run this code because the lattice is quite large, 1024 times 1024, okay. Yeah, if you reduce the lattice size, then the time will be much less, say 512 by 512, okay. Yeah. Anyway, you can try it, okay. Yeah. You can see my run, okay. Now it's running, okay. Yeah. And it's using the one GPU, okay. And then you go to the two GPU cases. And there's a two different declaration, X direction and Y direction. Okay. Okay, so I think I should stop today, okay? And yeah, and we will continue, okay? And yeah, next time, okay?
老师
Yes.
你没有把你的范例程式码放到我们可以看的地方，你放在你自己的资料夹里面，我们看不到。
你说我刚才没有 share 个 screen 给你们，有没有？
有，你有分享给我们。我是说你的程式码没有放在那个
有啊，有放在这边呢，有啊，没有吗？我看看啊，
没有，现在没有。Home CUDA Lecture 2024
Lecture 2024 OK。Oh, I see. Okay. Let me copy it. Pass. Okay, so you should see it now. Yeah. I thought I already copied it.
Yes.
Okay. Now you can see it. Okay. Okay.
Yes.
The entire direction is here. Okay. Okay. Yeah. Thank you for inviting me. Okay. Yeah. Okay. Any other questions? Okay. No. Okay. Then see you guys next time. Okay. Bye bye.
Okay, see you.
Bye bye.
Bye bye.